So let's start at the beginning. The NES is a pretty simple machine. If you look at what it is compared to systems that were available at the time, I mean, it wasn't super powerful. It was a 1.7 megahertz processor, and especially by today's standards, I mean, it's a pretty underpowered uh, machine. You have machines in the 1, 2, 3, 4 gigahertz range with multiple CPUs, and at the time even that wasn't super powerful. But by comparison, it's a huge factor of difference in performance. But what's kind of cool about the way that the NES worked was that it is similar to how sort of a modern system works, where you have the CPU and the graphics card. On the NES, you had the CPU and the what was called the PPU, and the PPU served the purpose of displaying the graphics on the NES, and did that in parallel to processing on the CPU. So let's kind of start with a picture of how this all works. So I like to think about it this way. You have the input on one side, you have your output, right? On the other side, here's your TV. Back when you had the original NES, hopefully you were running on a CRT. Hopefully today you still are, but a bunch of cool systems out there that'll work on newer HD TVs like the retro USB ABS and the analog NT Mini. But anyway, so you had your signal going to the TV, you had your input, which is your gamepad, and then you had the actual system in the beginning, in the middle. And so the system in the middle consisted of, you had your CPU, which also had the audio processing unit on it. You had the picture processing unit on it. And the CPU and APU and the PPU fed to the TV over RF or composite, and that's how you got your game showing up here. And the input went in to the system and processed through the game logic, came out the other side. So pretty straightforward. You also had your cartridge here, right? Whatever game you were playing, CPU had access to that. PPU also has access to that. What's really interesting about the way that this works is that the PPU is wired to the cartridge so that it can get information about the graphics from the cartridge directly. And so you end up having this communication, this two-way communication of the CPU and the PPU talking to each other about what needs to happen, not unlike a modern day graphics card where you would say to the graphics card to load a texture from system memory to the graphics card, but unlike that, you're talking about a much more limited system where it's loading it directly from the ROM, from the circuit board directly on the cartridge. Now there are some variants of that, and that's not something that I'm even knowledgeable enough to talk about right now. There are capabilities such as something called bank switching, which at its simplest we'll talk about in a little bit when we look at the graphics and what that looks like when you're developing for the system. But there are a lot of really interesting techniques that programmers used to expand the capabilities of the NES well beyond what you would have thought initially for such a sort of underpowered machine. So, especially if you compare it to, again, PCs even at the time, PCs generally didn't have this kind of picture processing unit. Yeah, they had a VGA card and stuff like that, but the difference was that for a PC at the time, you had your x86, for example, and it was doing your CPU logic for the game. It was doing the main game engine logic. And then what it was doing in addition to that is, so, you had your RAM where you had your game state, right? But then you also had your video RAM that you had to populate for the graphics that you were going to be drawing. And in order to do that, you actually had to calculate both on your main CPU. And so you were processing your game logic and your graphics logic all to render out to VRAM. And so you had these techniques that are slightly different from what you would do on the NES in terms of things like double buffering and off-screen rendering, which you can't really do with the NES because of the way that it's built, and we'll get into that in a second. But you know, in that sense, the NES is actually really a pretty powerful machine because it has built-in functionality for graphics that the PCs of the time didn't really have, at least not, you know, in consumer PCs. You generally just had your VGA, CGA, EGA card that was capable of displaying graphics, but not in the same way that the NES does. So how does this all kind of come together, right? You have all of these things fitting together to make your NES, right? That's your NES here, or your Famicom if you're in other places in the world. So how does that all work? So the NES uses a technique called memory mapping, which isn't unique to the NES, but what's really cool about it is, again, the way that it works is really pretty smart, and again, not too dissimilar from what they eventually did on the Game Boy Advance and the Super Nintendo, and I believe the Nintendo DS and the N64 moving forward. But because you had direct access to the hardware, you had to somehow be able to instruct it how to do what you wanted to do. So, for example, if you wanted to draw a sprite on the screen, you had to be able to tell, the CPU had to be able to tell the PPU that you wanted to do that. So how did that all work? So in the NES, there is memory, right? RAM, basically. Now, the 6502 processor, which was a pretty popular processor at the time and used in things like the Commodore and the Apple II and the Atari systems, it's capable of addressing 64K of memory. But the NES only had 2K of memory, so you know, it might have seemed like possibly a waste to have all of that additional address space, but what's really neat is this concept of memory mapping allowed developers to access the hardware in a very simplistic way. So let's talk about that. So here's your memory. If I can draw a straight line, here's your memory, and the NES only had 2K of memory, right? And so that was memory address range 0 to 7FF. That's your full 2K. So now what's all this other address range that goes on beyond that? So there is an area that mirrors the first 2K, and it goes all the way up to address 2000 hex. Okay? And so 2000 hex is where we get some interesting stuff happening. So the 2000 range is where you start talking to the PPU registers. So basically, if you think about it, you know, sort of as like wiring, right? The CPU over here wants to talk to the RAM to be able to do work, right? Your variables and your game state all sit in there. But it can address more RAM than is actually present. Now the PPU is connected in to the hardware that the CPU is using to talk to the RAM. And what happens is when the CPU tries to read or write to this memory address, for example, the PPU intercepts that request and goes, oh, that's actually for me. I need to do what it's asking me to do. So I need to either read from that address or write from that address. And the different addresses have special meanings, and we'll get to that because I don't have them all memorized. And that's the nice thing about the internet is you don't have to have them all memorized because, you know, it's readily available. I'll show you where. And so this is, again, a mirror of the memory above for the PPU. And then when you get to this range of 4000, you have APU and also I/O, your controller input. And it's the same thing. So the APU, although it's technically part of the CPU based on what I was reading, is also listening along this memory bus for requests to specific ranges of address so that it can get the requests from the CPU of what needs to happen, like play the sound, change the way the sound is being played, stop playing it, various adjustments that need to happen at the time that your game is playing. Additionally, you have your I/O, your input for the game, and you have the controllers, and it's going to read the state of the controllers and give it back to you. And it does it in a really interesting way that's not that uncommon for the time, given the expense of hardware and storage and whatnot. So basically, it's a little complicated, but once you understand how it works, it's not too bad. And then beyond that, you have a range of addresses. Typically, you have something like 8,000 is where your cartridge ROM starts. And I apologize for my handwriting. It's pretty awful, and I'm not used to writing on a tablet, really. So it makes it a little tricky. And then the only thing kind of at the end of this address range that's of note at the moment is this area right before the end. So, normally the address range stops at FFFF in hex, right? Well, at least right now, when you're starting a pretty basic game, and there are caveats that I've read about it where you need to change this or things you need to do in order to accommodate for the bank switching, which we talked about earlier. You at the end of the memory range, you have 3 16-bit addresses, right? So that's 2 bytes apiece, which is 16 bits, right? And these addresses are for what are called the interrupt vectors. And the interrupt vectors are defined as you have your Vblank interrupt, you have your reset interrupt, and then you have one more, which I don't remember what it is, and I haven't used it yet, so we're not going to talk about it. Just know that there are 3. For now, there are other ways that you can get other interrupts, which are more advanced techniques, which we may look into as we build a game and as we need it. But for now, we're good with the Vblank and the reset. So the reset is pretty straightforward. Reset is basically you're putting in an address from your cartridge, which again may start at the 8,000 range here, and you're saying, this is where I want the NES to start reading from the cartridge when the reset button is pressed. So, you put the cartridge in, you're playing for a little bit, you hit reset. What it's actually doing is it's jumping back to that location in the memory, which is actually a location in the cartridge that contains instructions of how to initialize the game. And I'll show you what that looks like after we're done with the sort of overall architecture here. So the other one that's really interesting is the Vblank. And what's the Vblank? The Vblank, if you've never looked at this before, you should check out. There's this really cool video that the slow-mo guys have on YouTube that shows in super slow motion how old CRTs and even newer high-def TVs work in terms of the way they draw the screen. So basically the way that CRTs work is they have an electron gun that sweeps from the top left all the way to the bottom right, and it does it one line at a time, and a lot of times it does it every other line at a time in order to do it quickly. And when it's doing every other line at a time, that's called interlacing, right? And that's where those different modes come from, where you have a mode like 720p, right? Progressive versus 720i. So progressive means it does each line one after another, and I means it's doing it every other line. So old CRTs, they start at the top left, they'd sweep across and draw line by line all the way down to the bottom of the screen. And the Vblank is the period in between getting to the bottom of the screen, getting to the top of the screen, and before the drawing actually occurs. If you've done programming on the PC, that's usually referred to as VSync, where you're waiting for the screen to be ready to start drawing again. And then once you're done, once it's ready to draw, that's when you that's when you would start doing something like drawing a double buffer on the PC. On the Nintendo side, you would not be doing any of those updates unless you're trying to do complicated effects once the Vblank starts drawing, but instead you do it in this period between the end of the last frame and the beginning of the new frame. Now, how do you do that? Well, built into the system has an interrupt for Vblank. So what'll happen is you tell it where your code lives on the cartridge when that you want to be called when the Vblank occurs. So if you want to do your graphics rendering, your game engine logic, whatever the case may be, you can tell the NES, call my code at this location here. It's sometimes referred to as NMI, which is an abbreviation for something. I prefer to think of it as Vblank or VSync just because that's what I'm used to on the PC. You'll see it referred to really as both, although NMI is kind of the NES standard way of referring to it. So these three addresses live at the end of the address range in RAM, and you populate them in your cartridge, in your code, so that when the cartridge is loaded, the NES knows where to go to start, where to go when the Vblank occurs, and then your game runs. So, I did not figure out all of this information by myself. I should make that 100% clear. There are some really great resources that I'm going to be using as we go through this. So one of them is the wiki on NESdev. It is a great source of information. So there's the reference guide, which just kind of talks about all of what I covered in much greater detail. It is, make it a little bit bigger so you can actually see. It goes through all of the information about how the PPU works. It talks about the different parts of the PPU. It talks about the memory mapping that we discussed. It talks about some other things like mapper chips, which we'll get to when we need to. Right now, I'm working on the game in a way that it doesn't really need the mappers yet. I'm sure that we'll get to that as we start building more of the game. And then it talks about the CPU, and here's the memory map that we were talking about. And so here are, again, all of the ranges kind of laid out nicely in a table. And you can see, kind of how that's broken down, and it references the other parts of the wiki, which makes it really easy to kind of work through trying to figure out why what you're doing either doesn't work or how to do what you're looking to do. And then the other site is Nintendo Age. Specifically, their forums. They have a section called Brewery where people are working on homebrew games. There's a lot of people here doing a lot of great stuff, and definitely worth checking out if you're interested in programming. That's where I'm getting the information that I'm using. There's also a Discord chat server that's been set up, and talking to a lot of excellent people on there about how to do all of this, because as I mentioned in the beginning, I'm not an expert when it comes to the NES. I'm still learning myself, and I know enough about programming to understand how all of this stuff works at a technical level. But it's a different story when you try to actually work on it, and the emulators do a pretty good job of simulating what would happen on the real CPU, and so you know, there are times where what you're doing stops working and you made a simple change and you don't understand why. And it's nice to have these references available, and also nice to have people that you can talk to when you've been racking your brain and can't figure out what you did wrong. And then last, I also use this website just because it makes it easy for me to find the instructions, because my brain just naturally thinks of instructions in assembler using x86 assembly, because that's what I learned when I was younger. And so there's a lot of times where I will just inadvertently try to substitute in the x86 assembler instruction instead of using the 6502 instruction, and that will not work. All right. So just checking to see. I see people are watching. No chats in the chat room, but that's okay. Cool. So where am I right now with the game? Let's go with that now. So I'm using Sublime Text as my text editor just because I like it. It's what I'm pretty comfortable with. I also like VI, which is a more keyboard-based editor. It makes it easier to navigate in some circumstances, but at the same point, not sure that I really want to be using that for this. We'll see. I may end up switching, but for now, Sublime Text is fine. And I've been working on this for only a little bit, you know, here and there as I have spare time. Excuse me, but I want to kind of go through what this all looks like, and you know, at a high level, talk about how the game currently is functioning, why it works that way, and then we're going to do some programming where I'm going to move some code around and probably break it. So this is what the game looks like currently. I have a gamepad here, just this that I'm using. I'm going to have to restart this because it's not going to pick up the controller. All right, so still not picking up the controller. Oh, I unplugged the Bluetooth. Well, that doesn't work. You need the Bluetooth. All right. So let's see. That looks like it's connected. All right. There we go. So pretty basic. I've got a ship that moves around. It fires bullets. Looks pretty straightforward. There are some more interesting things happening on here than what you see kind of implies, and we'll talk about that as we go through the code, but I just wanted to show how that's working. And so yeah, all of this is in this code here. One other thing I should mention is, well, you know what, we'll get to that after we get through the code. So what is the code that's actually running all of this? So at the beginning of every ROM that you have in your system, whether that's something you're developing yourself or something that you've downloaded so that you can play it on your home system rather than on your own NES, is this header. And this header describes to the emulator how your game works. So this is the NES header, and it describes how much ROM you have on your system, on your cartridge for the game code, and that's what the PRG stands for. It's for your program ROM. So in this case, I've got two 16K chips, essentially, for ROM chips for the program ROM. I've got just one 8K character ROM chip, and the character ROM is for graphics. So if we go back to this for a second here, if you remember, I was talking about how the CPU and the PPU directly access the cartridge. So the CPU is wired to your whoa, that's weird. Using a pen on Sublime Text is odd. The CPU is directly wired to the program ROM, so it can access the source code that you've written. And the PPU is directly wired to the character ROM, the char ROM here, which is where your graphics live. So the graphics are part of the cartridge, but they're not necessarily directly accessible to the CPU. Now, I mentioned earlier there are some exceptions to this with things like bank switching, and there's even ways that you can use RAM on the cartridge that's programmable to update the graphics using some additional hardware that would be built onto the cartridge. And that's really another brilliant part of the way that the NES worked, and that followed suit with the Super Nintendo as well. If you're familiar with the Super Nintendo and the Super FX chip, that concept of putting additional hardware on the cartridge, and I don't believe it was unique to Nintendo, but they certainly used it to full effect. That concept of putting hardware on the cartridge to enhance the capabilities of the system was kind of brilliant, because it gave the systems that longevity to continue to put out games that seemed better and better as time went on, instead of really being kind of a fixed function system where once the hardware was out there, that was kind of all you could do. Now, obviously, there were limitations to that, but it was really awesome. So on the Super Nintendo, you had the Super FX chip and the Super FX chip 2 that allowed you to do really great 3D graphics. On the NES, there were a few different pieces of hardware that were available. Some of them dealt with this prog ROM and the char ROM, and dealt with the bank switching. So basically what it was is you'd have multiple sets of ROM chips on your cartridge that normally the CPU couldn't address, right? There was no way for it to get access to it because the address range just didn't allow for it. It wasn't wired up to allow for that. But what these chips did, they're called mapper chips, they actually changed the way the CPU talked to the cartridge. And so what you'd end up with is you'd end up with the ability to expand how your code was stored on the cartridge and write bigger games. So you'd have more space for code, more space for graphics, the ability to do things like put RAM on the cartridge. The most common usage of that was for save games. So, when you look at like The Legend of Zelda 2, any game that let you do saves, that was actually RAM that was built into the cartridge, and there's a battery in there. And if you've ever opened up an old NES cartridge where it's got a save game, there's a little 2032 battery in there, a button battery. And if you collect retro games, you'll know that those batteries have to be replaced sometimes because they go dead after 20 years, and then your save games don't work, or even worse, sometimes they go bad and then they corrode the circuit board on the cartridge, and then the game is unplayable. So all of that is, again, sort of chalked up to the ingenuity of the engineers at Nintendo when they designed the NES, and allows the game to be bigger. Now, I kind of got ahead of myself, but I just wanted to talk about what that actually, what these things were referring to and why they're important. Because later on, we may have to, for this game, change the mapper we're using so that we can get more graphics into the system, or have more code. I don't expect that that's what's going to happen with this shooter, because this is, again, sort of more for us to go through together, where I'm learning how the system works and we get something sort of basic working, and then once we feel good about how this is, we can start building a more interesting game, or maybe not. Maybe we'll just keep doing this. So at the next byte in memory, we are setting the mapper. So that was what I was talking about, the mapper that determines how the system is talking to the cartridge and the prog ROM and the char ROM, as well as the mirroring. So the mirroring on the NES refers to the way the graphics are organized in memory, essentially. and how that plays out when you're actually writing your game. So there are two ways. There's horizontal mirroring and vertical mirroring. So the horizontal mirroring is really good for games where you have the screen like this and you want to scroll this way, because the screen is the area where you can populate your graphics is very long, right? And so when your screen, the NES has built into it scrolling capabilities, and so it's almost like if you think about a camera, the camera is moving along this field, showing different parts of what's in memory as you scroll down. And there are some caveats to the way that works. We'll get to that in a second, because it's actually pretty interesting. Now, so that's the horizontal mirroring, because you're mirroring horizontally, right? There's also vertical mirroring, where you have two halves of this the video memory like this, and you populate your graphics in here, and you are horizontally mirroring the screen, and you have your screen here, and you're going to be scrolling, generally speaking, back and forth, left and right. So like Super Mario Brothers would have something like this, right? Because you're moving back and forth. You're not generally moving up and down. Now, where you get into trouble is if you want to do both. If you want to be able to do both, now, what the mirroring refers to is that if I have the letter A drawn out here, it's also here. If I want to move the screen this way, I have to now update this part of the screen, which is the same thing as this part of the screen. So as you update, you're going to see changes occurring on the left-hand side because it's mirrored. Same thing with this. If I have the letter B and the letter B, and I decide I want to scroll in this direction, if I now start updating the graphics here, because it's mirrored, I'm going to see that at the top as I'm scrolling down. And that's anybody who's played an NES game is familiar with those weird sort of graphical glitches that you get when you are working on the NES. You see things appearing in the corners and whatnot, and so that is an artifact of that motion, and especially that'll happen if you want to go diagonally, because diagonally now you're not only updating the screen, you're not only having to deal with moving down the screen like this, but you're also having to do that update over here, which then reflects here, and it gets very tricky. Now, there is a mirroring called four-screen mirroring, where you actually have four distinct screens here, and the screen can move around across very smoothly. And for most games, this wasn't what was used, just because I believe the hardware was very expensive at the time. If you look at it now, it isn't super expensive, but at the time, all of the space, the RAM, the chips, all of that stuff was pretty expensive, and so they were looking to make these games as cheap as possible, and so they tried to restrict it to the most basic modes as they could. Seeing some chats here. Let me just stop for a second. So, is it possible to ever look at sources from other games? All right, so NEScoder responded. Yeah, so thanks to NEScoder for responding to that. So all of the code that you're going to be looking at now, that's not 100% true, because there are games that are written in the C programming language for the NES. But all the code we're going to be looking at here is written in 6502 assembler. And that was, I believe, the most common way that these games were made, just because the CPU was so slow. You really needed to be coding as quickly, or you need to be coding as close to the hardware as possible. You couldn't afford to let a compiler try and figure out what you're trying to do and maybe generate code that was efficient or maybe not. You actually had to generate it by hand. Now, certainly compiler technology has gotten better over the years, and with faster machines, it's possible to do better analysis of the code to try and figure out more efficient paths. I know there are a number of homebrew games that are now made in C, but I still think the majority of games are written in assembly. So now there are these additional bytes here. I don't recall what they do, but one quick look at the wiki on NESDev would certainly tell us what that's used for. So if we go to the reference, I'm just doing this one time to kind of show how to navigate. Here's the NES 2.0 format, and if we look at the bytes, we were at bytes 7 and 8. So byte 7 is a second set of flags to talk about, let's see, some of the mapper information, as well as some other stuff, play choice 10, and some other things we're not interested in, I guess, for this. And then bytes 8 through... Am I looking at the right information? Maybe I'm not. Oh, okay, so let's see. Perhaps I'm looking at the wrong information. I think I'm looking at the wrong information. So be prepared for for this to happen as we go. Like I said, I'm still learning. Yeah, okay, so I was looking at the NES 2.0. This is the iNES format. That's right. So the iNES format is different than the NES 2.0 format, and while the NES 2.0 format is technically better because it gives you more precise controls over how the emulator should be emulating the system, because it has to do the job of emulating the hardware that would be running the game as if it were on a cartridge. So for example, if the game needed work RAM on the cartridge for additional storage or additional graphics, the emulator has to simulate that properly. So it has to know which mapper you're using and what additional things you might need for your cartridge to work. So yeah, so 7 and 8 are essentially the same, not really all that interesting. Flag 9 is whether or not it is an NTSC game or a PAL. I have it set to 0 because we're doing it for NTSC. And then there are some additional filler bytes at the end here. Okay. So that's just the basic header of the cartridge in order to make sure that the emulator knows how to run the game. And then we start getting into the actual meat of the code. So I've defined a few constants here called, there's no entity, there's player type, there's bullet, and there's flyby, which is currently unused. So these are just some constants I've defined for the different types of players in the, not players, things in the game, the different entities in the game. This is a definition of a structure. So basically it's telling the assembler how my current game entities are structured in memory. Right now it's super simple. We have the X position on the screen, the Y position on the screen, and the type of entity it is, which would be one of these guys. We have a startup segment, which isn't being used. We have a 0 page. So the 0 page is a special area in memory, and it's special because of the way that the 6502 processor addresses memory. So if we go back to this page here, where it talks about the different, whoa, that was way too much zoom, where it talks about the different instructions for the 6502, what you'll notice is it has a couple of modes. It has an immediate mode and a 0 page mode for when it's addressing memory. But we can what I'm going to say is that we'll probably, I'm not going to spend too much time covering assembly language here on the stream right now. It's something I can do in a future stream, but hopefully you can follow along. If we have to, we can go back and do a stream of just how 6502 assembler works, so that people kind of get a sense of what that looks like. So the difference between immediate mode and zero page mode is maybe not apparent to someone who hasn't really done much programming on such a low level. But what you'll notice is that all of these instructions kind of call out the different types of ways that they address memory, and how big they are, and that's the number of bytes that the instruction takes when it's assembled by the assembler, and how many cycles it takes. Now, the ones that say 4+, those are saying, you know, it may be 4, it may be more, depending on what you're addressing when you carry out that operation. And so you'll notice that the immediate mode operation and the zero page mode operation have different timings. And depending on the instruction, you can see that in the case of this, for example, zero page is slightly more efficient because it's fewer bytes and one less cycle in this case. And on a modern CPU, you know, one cycle, who cares, right? That's sort of the predominant thinking amongst developers, unless you're a super hardcore game developer, right? Why did that start? Probably from my zooming mishap before. But if you're programming on a system that's only 1.7 megahertz, every cycle counts, and I'll talk about that in a minute, because I'll go through how my game is currently drawing on the screen and talk about something I messed up and how that impacted the way that the game rendered because I was taking too long. So yeah, every cycle counts, and there are different ways to address the memory with all of the instructions. And so, you know, this kind of reference is extremely important, especially when you're trying to optimize your code to eliminate as many cycles as possible. You know, going through this, we're not going to go too crazy about trying to always be super efficient, because right now I feel like the simpler I can make the code, as long as it's running, that's going to be more important than trying to make it super efficient right away and convoluted when I'm still learning it, and we're still kind of going through it together. And then I don't know what's wrong and what's broken when I'm trying to debug problems. So I just wanted to call the attention to this, just so that it's something that we're all aware of. You have these different instructions, different ways of addressing the memory. And so zero page refers to memory that is within the first 255 bytes of memory. So that is the range of 0x00 hex to 0xff. And so those addresses can be referenced in a more simple way by the CPU, sometimes taking less bytes and less cycles. And so that memory is a lot of times reserved for things that you're trying to do that you want to make more efficient. So, curious how this is. I have the chat and the streaming on another monitor here, and it's interesting how it's sort of not refreshing the way I would expect it to. I've streamed on YouTube before, but not on not on Twitch before. So anyway, all right. So let's go through. So the memory that I'm using here within the 0 page, I've got the controller, a single byte for that, and that stores off the state of the controller. The controller is actually read in 1 bit at a time. So if you have, if you remember before, I was saying that the controller is kind of interesting in terms of how it works compared to what you might expect. What is going on here? There we go. So typically you might expect that you get, you have just a bunch of memory that represents your controller, and it's got the A, B, the start, the select, and the directional pad, all 1 byte or something like that, right? God, my handwriting is bad. All right. So you have 1 byte, right? You might think that that's how it works for each button. But at the time, doing that was pretty wasteful. For every one of these bytes, you'd be wasting 7 bits. And then you could also say, well, okay, if I don't want to spend 7 bits per button unnecessarily, then I could maybe pack the bits into a single byte, right? Because there's the A, B, start, select, and 4 directional pads. That's 8 buttons. And so you could say, okay, so 8 buttons, 8 bits, perfect, right? Here's my byte. 1, 2, 3, 4, 5, 6, 7, 8, and then we'll get rid of this extra, right? And so now you have A, B, right? Start, select, blah, blah, blah. But again, hardware was expensive at the time, and so what they did was they used what's called a latch on the controller. So what you have to do in order to get controller state from the system is you have to first read from an address, and then you have to write to an address that says that you are going to be reading from the controller. And what that does is on the controller latch, it saves the state of the buttons. So let's say you're in the middle of the game and you're moving the D-pad and pressing the A button. When the CPU writes to that latch register in memory, it's saving off those buttons were pressed. And then from that point forward, you read from another address, which reads in every button state bit by bit. So what that looks like in your code is you say, okay, I'm going to write to this 4016 address. I'm going to write a 1, and then I'm going to write a 0 to 4016, and that's going to tell the hardware that I'm ready to read the controller. And then you read from 4016 after that. So we've just written to it twice, and now we're gonna read from it, and it's going to put it into the processor. And what it's going to do is if you get the first value off it and the A button was pressed, what you'll see in the processor is that this is 1 and the rest is 0. If it wasn't pressed, it'll be 0. And then the next time you read it, if the B button was pressed, it'll be 1 here. And then if it wasn't, it'll be 0. And you do that 8 times, and you get 8 different values in here that represent the 8 different buttons that could be pressed on the system, right? And so the problem with that is that you don't want to store 8 different bytes for 8 different buttons, and so you have to essentially yourself load in. So like if I said A is pressed, but the nothing else is pressed, you really want it to be that, it's 1 here and 0, 0, 0, 0, 0, 0, right? So I am 1 bit short? I'm 1 bit short. So you have now that A is pressed, but none of the other buttons are pressed, right? And we'll look at how that works. But the point is that I am then storing that representation of the controller here in a single byte. The scroll X and scroll Y, that's where I'm storing how the screen is scrolling in memory, because I want to do, so if you go back to this, you can see that the background stars are scrolling. And so that's using the scroll registers to do that, and I'm maintaining the value in these variables here, and then it's later updating those registers. I have a constant here that says how many possible entities, how many possible of these guys are in memory. I have a memory location that I'm allocating, so I'm saying I want to reserve memory up to 10 entities times the size, right? Because we need these 3 bytes times the maximum number of entities. And then I also want to store off what the total supported entities is currently. This is hard-coded just because, again, kind of getting started. So I've got the max entities, I've got the size of, I'm calculating what the total size looks like, right? This button flag we're not going to talk about because it's not really important right now. This swap memory address this is related to how the background scrolls. So if we go back to, and I apologize there's a lot of back and forth, but I'm trying to cover a lot of stuff here as we go, as we work through this, and so it's just kind of a necessary evil of starting from the sort of beginning. So, right, so you have the screen here, and I told you can scroll it up and down, left and right, and the hardware allows for that. The problem is that the screen, the scroll register, only allows for 255 possible values, and the screen, the total height, this isn't to scale, because it's actually, let me fix this so that it's an accurate representation of what that looks like for real. So yeah, so there are essentially 2 full screens here. So if this is 255 pixels, this is also 255 pixels. And the problem is that you can't scroll past 255 pixels. Why is that? Because the scroll register is only 1 byte, which means that the maximum value it can hold is 255 as a positive integer. And so if you try to add 1 to that, it becomes 0. Okay? And so what will happen is you get the top of the screen, for example, if we're scrolling down this way and we're going 0, 1, 2, 3, all the way to 255, and we hit this point and we're at 255, we go back to 0, instead of continuing on, it's going to jump back up to the top, right? Because the value has rolled over from 255 to 0. So what you have to do in that situation, if you want to continue to scroll down this portion of it, there is a register, there is a value that you can write to the PPU to tell it that the scroll register no longer is referring to offsets from here, but rather to an offset starting midway down. So essentially, rather than having that 255 limit, you say, okay, at the beginning, I have my position 0, that I'm going from 0 to 255, right? And then when you hit the 255, it's actually a little bit shorter than that because of the way that the scrolling hardware works and the screen works, but when you hit the bottom of the screen, you then say, okay, I'm actually now going to go to position 1, and again from 0 to 255, allowing you to scroll the full position, the full width or height of those screens. And it works the same way for scrolling horizontally. You can only get to this point, and then you have to update the PPU to tell it that you're changing the offset from this first position to the second position. So hopefully that makes sense. And what I can do is I can show you that in the emulator. So if you look at the what's called the name table viewer, it's doing a really janky job of showing that, but if I kind of click on it, you can see, so you see that line going horizontally, it's kind of crawling up the screen. So that's the vertical scroll register getting updated, and then when it hits the top of the screen, I'm swapping the offset so that we're starting at the very bottom there. So what looks like a pretty continuous scroll is actually just scrolling around and around and around, almost like if you imagine just a sort of a roller system, like if you could imagine that, and you have paper kind of just rolling along, right? And it's just the star background. I mean, super basic, but it was just again to make it do something rather than just having a black background where nothing is happening. So this swap location in memory is keeping track of which offset should be used as we scroll through the background. These other memory locations, let's not worry about those right now. This seed location, that's for some randomizer code that I got off of, I believe it was NESDev, I think. Someone pointed us in that direction, and it seems to work well enough. This flicker variable here, this is just a counter, a simple counter to determine when it should make the color for the ship actually do that little bit of flicker that it's doing for the little the cockpit. I don't know if you can see that on the stream. It kind of flashes. I just thought that was a cool effect. I don't know what made me want to do that. And that's all how the memory is organized. And now we're actually into this segment here called code, and all the segment is just a way of dividing up your program into what's in memory and what's the character ROM for your graphics and what's your program ROM. So you can see there's the header segment, which is at the beginning. There is the the 0 page, which is organizing the memory. That's actually in the RAM. And now we've hit the code where we've got some stuff that is actually going to happen and actually runs the game. So this is that random number generator that I was talking about before. I'm not even going to get into it. I don't necessarily even know how it works because I didn't really look at it. It was just something that I pulled because somebody said it worked, just to kind of keep it simple. We can always come back and look at that. This was just to keep it simple for myself, rather than trying to write my own random number generator and do a poor job of it. This is a subroutine. This is waiting for the Vblank that we talked about. Now I don't really use this anywhere except for in startup, but it is waiting. It's looking at the hardware to determine when we've gotten to the point where we are waiting for the new screen redraw so that we can start updating the graphics and building our scene for the game. And then we're actually into the reset here, and this is what gets called when the game finally we're here, the game gets started by the NES. So if you look at the this section here, it's a segment called vectors, and it's what I was talking about before. You have the Vblank vector, which is what gets called when the screen is ready to be is getting ready to be redrawn but is not drawing currently. You have the reset vector, which is what gets called when the system gets reset, and there's the third one, which we're not using at all. So if I go back to my code for reset, this is all pretty much boilerplate. This is something that you wouldn't be writing over and over again, but we'll definitely just kind of cover what it does. So we're initializing the system. We're turning off interrupts and turning off things that aren't necessary and getting things initialized. So turning off decimal math because it doesn't work on the 6502 that the NES has built into it, so we just have to turn that off. We're turning off audio interrupts here so that we're not going to get any sounds or anything. We're initializing the program stack. So the NES, the 6502 does support a stack that you can push and pop things off of. It's called a push and a pull on the 6502. But if you're familiar with programming, you're just basically setting the location that the stack begins at. So we are setting, we are setting the location of the stack. Where is that code? We are setting the location of the stack to FF, and we're doing that by loading the value FF into the X register. We're then transferring the X register to the stack register, which is what effectively tells the CPU where the stack lives currently. So if you look at it sort of as a traditional stack, you have your FF, and then every time you push onto the stack, it grows downwards, so you're going into lower memory addresses. Then you increment X, and because it's already at FF, which is 255, it becomes 0, which is the value that we want to store into these memory addresses, which are really the CPU and audio registers. Once those are stored so that we've turned off all the CPU, all the graphics rendering and all the audio playback, we want to wait for a Vblank. We want to wait for the screen to wait for the picture processing unit to get to a point where it is starting to try and draw the screen. This is, again, very boilerplate, not something that you'd be writing every time. It's just something that your game should do in order to ensure that it is working properly. From that point on, we know that the X register has the value 0 in it. So we're going to put that into A because we want to use the A register to 0 memory. So basically, again, this is all kind of stuff that you kind of have to just write once and keep it as a template file somewhere. We're looking at this memory address range, this 2K of memory, and at startup we're going through and zeroing all of those values in memory out because we don't want random junk in there. We want it to be a known good state. We are skipping, notably, the range 0 to 100, and the reason we're doing that is because that's where information about our sprites, our actual graphics for the game are going to be stored. So we are zeroing out everything. We are zeroing out all of the ranges of memory, except for that one. We are storing FF because when we transfer this memory at 0 to 100 to the PPU, which we'll talk about how that happens in a minute, we want it to be all F because that will just essentially make the sprites non-visible on the screen, which is what we want. We don't want a bunch of weird random sprites showing up in random places or in the top left corner of the screen. We want them to be off screen and non-visible. So we put that into the A register. We store it at the 0200 location, and then we just keep doing that. We are using X to index into these ranges of memory. So the X register can be used to index in, meaning that if you say that you are addressing memory address 0 and X is equal to 0, then you are actually directly addressing address 0. That's a lot of it, the word address. But the point is that if you add these two things together, you get the final address that you are writing your value to. So if you were writing a value of 1 in there, the value of 1 would be written to the 0 memory address. If you then have X is equal to 1, the next time you call this, instead of it writing into the 0 address, the 0 address that's in the left part of the call here is added to the X register, giving you memory value. Come on, 0, 0, 1, and so on. And you do that count from 0 to 255, which is FF in hex, essentially allowing you to traverse a memory address range without having to, hard code that into your assembly. If you've ever programmed before, if you've used an index where you've done something like, for I is equal to 0 and I is less than, some number where you're incrementing I, right? And then you're saying my thing, I do something, right? It's the same thing, essentially, to a certain extent. Your I is essentially the same thing as the X register. It is an index into a location in memory that allows you to perform loops. All right. So once we're done clearing out the memory, we're going to initialize the entities in memory. We're going to initialize the player. So the player type gets stored here. And then we're going to clear out all the rest of the entities, and we're going to say that we want to, we want to store them off screen and that their entity type is 0, which is that there is no entity there. Because what we're doing is we're basically writing essentially an object management system. So each different thing in the game could be considered an object, essentially, right? Your player, your enemy, the bullet, and each of those is represented in a location in memory, which is this entities range here in memory. And so when you hit the button to spawn a bullet, it's going to add it to this entity range, and then what we'll do later on, you'll see, is we will populate memory. We will populate sprites according to which of these entities is actually live and active. If they are not active, then there is no need for a sprite for it. So we're essentially putting together an in-memory representation of the game that's separate from the hardware representation of what's actually happening. All right, so the next thing we're going to do is we're going to clear out. We have to essentially tell the registers in the PPU. We need to tell the picture processing unit that the next thing we want to do is store information about the color palettes that are used. So the color palette system on the NES is a little bit different than kind of what you might expect. It is a fixed system of colors. I'm going to steal NES Dev's mapping of colors just because it's simpler than me trying to do anything there. It has a fixed set of colors from this palette. So these are the choices that you have to work with on the NES. These are the only colors that you can display on the NES. And there's some other things you can do to make the colors look different. There are bits that you can set in the register for the PPU. So you can tell the register, I want to emphasize red or blue or green with all the colors that are displayed. So basically you can, if you have a blue, you can make it look super blue by setting that bit. Or if it's something like a purple, you can make it look a little more red by changing that emphasis bit. And so it's a way of sort of messing around with the colors and making it a little more interesting. But basically, these are the colors you can work with, and then in addition to having those colors be available, you're limited to only a certain number of colors. And if you look in the emulator here, you can see in the viewer of the PPU, I'm going to pause the emulator for a second. You can see that there are these colors here. There are 64 total. Sorry, I can't do math. There are 32 total colors. Right? I did that right? 16? Yeah, 32 colors. And there's the caveat that those colors can only be displayed 4 at a time. There is a more complex explanation to that, but let's suffice it to say that it's 4 colors at a time for now, with some exceptions. The sprite 4 colors are separate than the background 4 colors. As we need to deal with that, we will get to that because this stream is running longer than I expected it to already. So we have to load in each of these individual colors to make the game show the graphics the way we want to. So that's what we're doing here. We're essentially resetting the PPU to load our colors. And so if you look at this part of my cartridge, or of my code, you can see that I've got all of these cryptic hex values here, but all those are the actual colors I want displayed. So for example, the 30 color is this white. 0C is this dark blue. And so I'm just loading that into the graphics, the PPU, so that it will have the right colors for my game. All right, so done loading that. Now I'm going to essentially initialize the background to display the star field. And so the way that works, the NES isn't actually capable of drawing graphics like the PC was, in the sense, or even modern systems are, where you have what are called essentially raster graphics, where you can draw pixel by pixel. Instead, the NES worked using 8x8 tiles. So all your backgrounds, all your sprites, everything that you display on the system has to be an 8x8 pixel tile. So that 8x8 tile, if you look here, again, really simplistic because I'm just kind of starting with this. The 8x8 tile, the tiles that I've defined are, you've got the star field here, which is just individual pixels that are kind of wasted on an 8x8 pixel because it's 8x8 pixel tile because it's just one pixel in each of them. And then you have the sprite tiles, and here you have half the ship and also the bullet that's being fired when you press the A button. And so why is it only half the ship? Well, the interesting thing about the way the tile system works is that the NES, it may only work with 8x8 tiles, but will happily draw those tiles either horizontally or vertically flipped. So in the case of the ship, I've only got half the ship stored in memory, but because it's symmetrical, I can draw the other half by just drawing the same tiles flipped horizontally to make it super easy to store that efficiently. And then I've got the bullet, which is just an 8x8 that gets fired from the ship. when you press A. No, I don't want to run turbo. I just want to run normal. Come on. Right, so, oh, my controller is once again not connected. Anyway, so you can see the stars, you can see the ship there. And then all I'm doing here is I'm essentially loading up the background with the star field, using that random number generator to just generate a random star field. It just seemed like the right thing to do. I'm not going to go too far into this just now. Again, the stream is running longer than I wanted, and we'll get to that next time, and maybe we'll actually do some coding next time. And then finally, once that's all loaded into memory, we're going to wait for the Vblank again, because we want to make sure that the screen is ready to draw before we start turning on drawing, because up at the beginning we loaded up all of this stuff in memory with the drawing turned off. When we set the values of these memory addresses here, we were telling the PPU, hey, don't draw anything, because we weren't ready, right? So we waited for the Vblank here. We did all of our initialization. And then we waited for one more Vblank so that we were making sure that we were turning on the drawing when the screen is ready. And once that Vblank is done, so we're back at the top of the screen and ready to draw again, we turn on the PPU and tell it to render the sprites and the backgrounds, and we do that by using these control registers for the PPU. And so each of these bits has a different meaning. And if you look again at the NES dev, you can see that controller 2000, that's the first one we write. We just set the first bit on, and all we're doing is we're telling it we want to be notified that the vertical blank is starting, right? So that we can start drawing the screen. And then for 2001, we're setting up what we want rendered and how. So we have turned on bits 1, 2, if this is the first bit, so we have bits 2, 3, 4, and 5 turned on. So going back to this, we are saying we want the background in the leftmost 8 pixels of the screen. We want sprites in the leftmost pixels of the screen. We want to show the background. We want to show the sprites. And then we are not turning on any of these emphasize bits, right? So like I was saying before, you can do sort of interesting color enhancements by turning those on. We're not doing any of those. We just want the standard color palette. And then we have this jump here where we're doing an infinite loop because the rest of our logic is here in the Vblank. You can see I have a note here because all of the logic is here, which is not great. I ran into a problem where originally I was handling all of the logic that was being done for processing the controller, which I've moved to the bottom. After this done with PPU part here, I was handling all of this stuff before I was trying to update the PPU and draw the graphics. And what I found out was that that code was taking too long. And then as a result, it was doing this weird thing where it was actually partially updating the screen, but not updating any of the sprites or any of that stuff because I was taking so long. And so in the emulator, I was able to it has some cool functionality where you can write code outside of your game, and you can add the ability to time how long your code is taking. And so you have about you have just over 2,000 cycles, I believe, to complete everything before the PPU starts drawing the screen again, and I was taking well over that. So at this point, we're at 1,080, you can see, or 1,100, pretty consistently, which isn't bad. I mean, you know, I don't know what's typically considered good for this. It's just, you know, working at this point. So I'm going to call that good enough for now. But what I'd like to be able to do is move all of the logic that happens related to the game itself out of this part here and leave only the drawing logic within this Vblank. So That's what I was hoping to get to in the stream today, but I'm at an hour and a half, and I haven't, and I kind of just barely scratched the surface of what's going on. And I think what I'll do is I'll save that for next time, and we'll actually do some coding here instead of me explaining a whole bunch of stuff. I didn't realize it was going to take that long. But hopefully this was interesting and useful, and if you if you have any questions and you're in the chat, I think there are a few people maybe still in the chat, but if not, then if you are watching this afterwards, I'm on Twitter at Clearvis. I'm also on NESDev. I'm on Nintendo Age, and hopefully this was useful, and if people want me to, I will do an assembler tutorial talking about how assembler code works before we get into more of the game stuff. Otherwise, I'm going to go into separating the game engine portion of the game logic portion of what this is doing from the actual drawing logic, and then continuing on with making the game. So that's it for tonight. Hope you enjoyed it, and the plan is to do the next stream at on Thursday at 9 Eastern again. See you next time.